types of bilirubin. There's unconjugated and there's conjugated. So what it does is it takes this conjugated bilirubin from the liver and it basically starts to go through the bile duct, and you've got the bacteria in the intestines that break down that conjugated bilirubin into basically urobilinogen. It even breaks it down into a substance called stercobilin, which is what causes your stool to be brown in color. Okay, so they do test urobilinogen levels, and there's a picture on page 86 that tells you basically how the urobilinogen ends up getting into the urine. After it goes from the liver, it goes to the intestines, the bacteria convert it to urobilinogen. Some of that urobilinogen goes on out and becomes excreted in the feces, but some of it gets reabsorbed, it gets back in the bloodstream, and it goes through the liver, and it ends up, very small amounts gets excreted in the urine. Okay? So there is a pad on the dipstick called urobilinogen, and most of the time they're more worried about, from what I've read about it, they're more worried about when urobilinogen is not present at all in the urine. But there's no way to detect that on the dipstick because it just basically gives you a result like 0.2 or 2. There's no way to tell if it's really not there, but if it's not there, that signifies that you have an obstruction in the biliary, okay, in the biliary ducts.
But you can only test for one type of the bilirubin in the urine, is that what you said?
No, well, it's conjugated.
Okay.
Bilirubin before it gets
I mean,
to
not
the
the
liver,
urobilinogen, I'm sorry, not the bilirubin.
Yeah, urobilinogen. You test for it in the urine. There's only one type of urobilinogen.
Okay, all right.
I was
They
just
can't
letting
tell
you guys
the
know
level.
that it's a
It's the level.
byproduct of urobilinogen that causes your stool to be brown. That substance is called, I think the book says it's stercobilin. All right, on page 88, under clinical significance of urobilinogen, I'm in the very first paragraph, basically on page 88, it says increased urine urobilinogen is seen in liver disease and hemolytic disorders. And if you go down to the last paragraph in that section, it states about the significance of not seeing any urobilinogen in the urine. Nitrite. That is the next analyte we will talk about. It's in the very last paragraph on page 88. All nitrite has to do with is if nitrate is converted to nitrite on the pad, it'll change color. It'll become a pink color. The main reason you need to be worried about nitrite is because that means there's a good chance there's bacteria in that specimen. Gram-negative bacteria, only the gram-negative, but gram-negative is generally the bacteria that is responsible for urinary tract infections, okay? But gram-negative bacteria have the ability to convert nitrate to nitrite, okay? So if we can detect that nitrite, more than likely that tells us there should be bacteria in this specimen, all right? Now, it may just be contaminated bacteria because that specimen has been left out at room temperature for a long time. But if you see that with white blood cells on the microscopic that we're going to talk about in the next chapter, that's a good indication of a urinary tract infection. Long story short, if your nitrite's positive, you should see bacteria in that microscopic, okay? Any place I've ever heard of, if your nitrite pad is positive, that's an automatic indication that you have to do a microscopic. And then generally, the way it all works, you may not ever know it. You turn that out as positive and you say you see white blood cells and bacteria on the microscopic, then the patient's physician, he or she, is probably going to order a urine culture, all right? Now, there's a lot more to this that you'll read about in your urine. For example, they can actually correlate if your nitrite's positive, that means there's more than like 100,000 bacteria, all right, in that actual specimen. But I can't go over all of that. I just want you at this point from today's lecture know if there's any pad on that dipstick that means bacteria, it's nitrite. It's the nitrite pad goes with bacteria. Okay, on page 89 in the right-hand column, under reagent strip reactions, it says the chemical basis of the nitrite test is the ability of certain bacteria to reduce nitrate, which is normal in the urine, to nitrite, which does not normally appear in the urine. Make sure that you have highlighted that what's called a Grice or a grease reaction in the sentence below that. Does everybody see that word, Grice reaction? Because that's the principle of the strip. And you can read about that reaction, but I want you to,
What page is that?
even if you have to, memorize that Grice reaction. You'll read on down 3 or 4 lines, that's where it tells you about the sensitivity of the test is standardized to correspond with a quantitative bacterial culture criteria of 100,000 organisms per milliliter. Another key point that I have highlighted in my book, probably for a very good reason, under reaction interference, the last section on page 89 under reaction interference, go down to number 1. It says bacteria that lack the enzyme reductase do not possess the ability to reduce nitrate to nitrite. Reductase is found in gram-negative bacteria that most frequently cause UTIs. Non-nitrate reducing gram-positive bacteria such as yeast can cause significant number of infections as well. So you could have a pad that does not test positive for nitrite and still see yeast, all right, on the microscopic. And that's one of the reasons, I think we may have talked about it, that's one of the reasons that if your glucose pad is positive only, some places they tell you you don't have to do a microscopic if that's the only thing that comes up positive. But then there's other places that tell you that you do have to do a microscopic because yeast love to feed on glucose, all right? It makes the perfect environment for yeast to thrive. So some of your diabetic patients, they also have a problem getting yeast infections because their urine is so sugary. Make sense?
Mm-hmm.
Page 90, leukocyte esterase. We're talking about anytime you hear the word leukocyte, that means a white blood cell. Under leukocyte esterase in the right-hand column, I'm in about the last 4 or 5 lines under the first section. It says an additional advantage of the chemical leukocyte esterase test is that it detects the presence of leukocytes that have been lysed, particularly in dilute alkaline urine, would not appear in the microscopic examination. So if you are testing a specimen that has a lot of water content to it, that means it's dilute, all right? And it's alkaline, the pH is say greater than 7.5. The white blood cells may have been there, but you won't see them under the microscope because they've been lysed. But the test will still come back as positive. So that's a good thing. That at least lets us know. So theoretically, you could have a positive leukocyte esterase on your dipstick and not see white blood cells underneath the microscope. Not very often, but it can happen. Under clinical significance, go down to about the 5th line down. It says the leukocyte esterase test detects the presence of esterase in the granulocytic white cells. That means the neutrophils, the eosinophils, and the basophils. It also detects it in monocytes, but not lymphocytes. It says neutrophils are the leukocytes most frequently associated with bacterial infections. It also states that esterases are also present in a parasite called Trichomonas. We will talk all about Trichomonas in the next chapter that we will be in about 10 minutes. Okay, Trichomonas vaginalis. That's a sexually transmitted pathogen. We'll talk about that, and I'll show you. I'll try to draw a picture of it on the board for you. One thing, make sure that you have highlighted on page 91. If you'll look on page 91 in the left column, go just below the arrows, and you'll see a sentence that states the leukocyte esterase reaction requires the longest time of all the reaction strip reactions. If you look at it manually, you're supposed to read the leukocyte pad at 2 minutes. It is the very last pad that you read. I think I told you guys that in the last lecture too, if I remember right. Right, specific gravity. We talked about this in the physical exam of urine, but I still want to go over it again. Just basically the reagent strip reaction for specific gravity. I'm on page 91 in the right-hand column for the reagent strip reaction for specific gravity. It says this is based on the change of a polyelectrolyte. That's the key word when you're measuring specific gravity, is that polyelectrolyte. What it does is it ionizes, it releases hydrogen ions in proportion to the number of ions present in the solution. Whenever you hear the word ion, usually I think electrolytes, anything that you see the pluses and the minuses by, okay? So when you think of molecules like chloride molecules and sodium molecules that dissolve the contents in the urine, that's gonna cause that pad to change color, right? The good thing about the pad over the refractometer that you guys looked at specific gravity is the pad is basically detecting ions, and it's not being affected, say, by urea molecules, those big molecules that the physicians really aren't interested in, glucose molecules and urea. They're wanting to know the concentrating ability of the kidneys. So the pad, in my opinion, is actually better than using the refractometer because there's things that won't cause a false positive, like radiographic contrast dye. Yeah. That will affect the refractometer, but it won't affect the pH pad on the dipstick. Most clinics you go to, they don't even have a refractometer. They take the pH directly off of the dipstick. Okay, before class, I was looking at all of these review questions. I actually had to test it out, and I was looking at everything just to make sure that we covered. There are so many review questions, but they are just about all of them are very good. I do want just to explain to you how the author of this book and most ASCP people, they really, for some reason, like to ask the principle of the reaction is, okay? And to prove that to you, I'm going to go through some of these, and I'm going to have you asterisk them, okay, on the questions that are asking about the principle of the reaction, the principle of the reaction, the principle of the reaction. Okay, now I'm going to cover a few other questions too, and this is probably going to take a little while, but I will tell you that your next test, because it's got to cover the chemical exam of urine, microscopic exam of urine, and it even goes into disease states, it's lengthy, okay? Because there are so many points that I got to get across to you between this chapter and the next one that I have to ask a lot of questions on. So you're liable to have 20 questions off just this chapter we went over, and another 25 questions off the microscopy chapter. I got to cover a lot of information on this. I can't just ask a couple of questions because there's too much information. I'm thinking that you guys go home and you read these chapters, because to be honest, I don't have enough time to present this the way I wish I could, right? Or we'd be here all day. All right, so some of these questions, go over all of them, but I'm going to go over the ones right now that are super important. Number 4, on page 92, the reagent strip reaction that requires the longest reaction time. C, leukocyte esterase. Number 7, the principle of the reagent strip for pH. Now, I know that I went over this a week ago, but this is one of those questions where you remember how I told you you need to know the little phrase that goes with each analyte, or a lot of them? Yeah, answer is D, the double indicator reaction. Number 17, the principle of the protein high pad on the multi-sticks pro reagent strip is D. It's asking for the principle of the reaction for protein. Okay. Let's see, the protein error of indicators. That little pad it's basically a pH pad, but the more protein that's in the specimen is going to change the pH of the pad, which makes it I know you guys have had a blood bank test this week and all that, and you probably kind of put this on the back burner. But again, when you're studying for this chapter, learn the principles of the test. You don't have to know the diagram of the arrows and all that, but be able to tell me, for example, double indicator system, double sequential enzymatic reaction, the Grice reaction. They each go with a different pad. All right? Speaking of that, number 23 on page 94. The principle of the reagent strip test for glucose. Anybody remember us talking about that last week? C, the double sequential enzymatic reaction. Number 25 is a real good question. The primary reason for performing the clinic test, remember that test I told you, the confirmatory test or the backup test for glucose?
D?
What's the answer to C? I'm not looking at it. Yep. It's an inborn error of metabolism.
C.
You remember me telling you guys about the story when I worked that any child that was less than 2 years old, you have to do the clinic test on. It's not one of those that you do the clinic test because the glucose was positive. What you don't want to see is a glucose pad that's negative and then the clinic test is positive. All right, that's what you don't want to see. So even if you do a dipstick on a 1-year-old baby, okay, and it comes out completely negative, a lot of places require you to do the clinic test. You don't want that to be positive because that's detecting galactose, it's detecting reducing sugars. It's not really worried about glucose. Number 35, the principle of the reagent strip test for bilirubin. That one's going to be, the answer to that should be the Diazo reaction, A. Number 35. Number 41, the reagent strip test for nitrite uses which of the following? A, the Grice. Number 44, all of the following can be detected by the leukocyte esterase reaction except
C.
Right, it doesn't detect lymphocytes. C is the answer. Basophils, neutrophils, and eosinophils, those are all considered granulocytic white blood cells.
Number 44.
Okay, lymphocytes are not. And I think in the reading we said monocytes will show a positive.
What?
Number 47, the principle of the reagent strip test for specific gravity uses which of the following? Remember I told you to remember that word polyelectrolyte.
Oh, you got
This is a
it.
polyelectrolyte that ionizes based on ions.
What letter was it though?
47. And it was C.
Number C.
Number C.
Mindy.
I didn't have this one marked, but this is a good question we talked about with last week too. Go back to number 33. A speckled pattern on the blood pad of the reagent strip indicates which of the following?
A.
Good, hematuria.
Yeah, 'cause
Remember,
it's
I told you
blood.
on a blood pad, if you have a change of color, that's positive, but if you see little polka dots in the pad, that's supposed to tell the tech, hey, there's a very, very good chance that there's intact red blood cells. Blood in the urine, the term for that is called hematuria. If it's blood that's been lysed, it would be hemoglobinuria, or it could actually even be myoglobin. Remember, there's 3 things that'll test positive for blood: red blood cells, hemoglobin, and myoglobin. Those are 3 things that'll show positive on the blood pad.
Don't the other two just make it change color just in general? There's no
It's a broad
dots.
color
Yeah.
change, yep. It'll go right to a blue color. But if you see polka dots, which generally that's what happens, it's generally polka dots that you see. Okay, so when you go back and look at that chapter, there's a lot to it. You need to know the procedure for dipping a urine. You need to know the 10 things that most dipsticks test for, and then try to go to every analyte and pick out things that separate it from the other analytes, okay? You're not gonna be able to know every single thing about every single analyte, but kind of go over what I touched on as far as importance level. Know the principle of the reaction, know things like, you know, whenever I think about white blood cells on the dipstick, the first thing that always comes to my mind is urinary tract infection, and it's the pad that's red last. Okay, that's just like two things that pop out at me. Bacteria, nitrite.
Yes.
Nitrite is what detects bacteria. Okay, the pH. The pH is, I mean, I understand the importance of it, and I want you guys to, I mean, yeah, it detects acid-base disorders, but it also, as we're fixing to talk about in the next chapter, if you see crystals in the urine, you look at the pH and that'll tell you what kind of crystal it is.
Okay.
We're gonna talk all about that here in just a few. Okay, as far as labs for this class, I used to do a lab every Friday, no matter what. No matter, I would just speed through the lectures and all of that, but I want to get through the microscopic exam. We've got 2 chapters that follow this chapter we're gonna go over today, that are based on disease states. This will be the first year I've ever did this, but I've already looked at the test and I know how many questions are off those chapters. And, I'm gonna have you guys kind of do a self-study of those chapters on your own. I'm gonna have you read it. I'm even gonna tell you how many questions are on the test from that chapter. And I'll even tell you which subjects to pay particular attention to. But I'm gonna have to have like a full lab so we can go in, because even though this book is important, to me, it's also really, really important that you guys practice dipping urines and that we look at picture after picture after picture of what's called microscopic sediment, okay? Because that's what you will do as a tech. You will never diagnose someone as a tech. You will never call the physician and say, look, I see uric acid crystals in the sediment, so you may want to call that patient and tell them they have gout. You understand what I'm saying?
Right.
You will never do that. Unfortunately, the ASCP test wants you to be the doctor, and that's the kind of questions they're gonna ask you. They're gonna give you case studies and give you all the information, and they want you to actually be the one that says, this patient probably has gout, or this patient probably has nephrotic syndrome, okay? But when you go to clinicals, I want you to impress those people when you go to a hospital, and I don't want you to feel intimidated dipping a urine, or feel intimidated looking at the microscope and looking at the sediment. I want you to feel confident about that. So we're gonna spend a lot of lab time looking at pictures, looking at the microscope, dipping urines, because I want you to get hands-on,
Yes,
okay? But you gotta give me your word that you're gonna read over those chapters about disorders, because there are so many of them. When you read it, it's gonna blow your mind, all the disease states that go with urinalysis results, okay? So I'm gonna try to get through the microscopic today. It is long.
What chapter
There's
is
no way I can
I
do
think
it
it's the next
the
one,
way I
so
wanna
chapter
do it, where I
6.
can go slow. I gotta go at a certain speed. You guys are welcome to ask questions, but just know, everything we're talking about, I'm going to reassure you or confirm it, because in the labs, we're fixing to start showing you pictures of these things. If you are real interested and wanna start studying early, YouTube. Google Images is the best way you can learn about urine microscopics. Type in, you can just type in urine microscopics and you'll see picture after picture that will show you real live pictures of all the stuff that we're fixing to talk about. For example, when I start talking about red blood cells, just so you understand where I'm coming from, we gotta talk about regular red blood cells, we gotta talk about crenated red blood cells, we gotta talk about ghost red blood cells. I just told you 3 different ways that red blood cells can look in urine sediment. It's that way for a lot of the stuff. There's not one set picture I can show you that says, this is what this will always look like, because so much of this stuff comes in different forms. So there's gonna be a lot of gray areas. There's gonna be areas where I say, look, if you see them and they look like this, it's a red blood cell, but you may see other ones that look like this, and those are red blood cells, okay? So you kind of got to put all the pieces together to understand that. And a lot of it takes time. A lot of it just takes you doing microscopic after microscopic after microscopic to determine what this stuff is. And then throw in that urines are different colors, okay? So even though the sediment from a urine that was red and clear, the things will be a different shade of color than the sediment from something that was yellow and cloudy. So you just gotta put that into the equation as well. All right, so we will start off, it looks like it starts off on page 100. Macroscopic screening. And in the left-hand column, go down to the last paragraph in the left column. Starts with the word parameter. Everybody see that word? Okay, you want to highlight it like 3 lines. It says parameters considered significant vary among labs, but usually include color, clarity, blood, protein, nitrite, leukocyte esterase, and possibly glucose. What they're telling you there is that's the order they're going to give you that indicates you have to do a microscopic, okay? Anything that tests positive, for example, and again, I'm always going to go by where they did it, how I worked, but if you had a urine that was any other color other than yellow, pretty much, we had to do a microscopic on it. That's what kind of like reflex testing, okay? So when it says color, that's just telling you that any abnormal color, you're required to do a microscopic. Even if you have an abnormal color, let's say it's red and cloudy, but you do the dipstick, and even though it won't, everything's negative, you still have to do a microscopic on that specimen because the color was red. Right? Clarity. Pretty much anything that's not clear is required microscopic. Blood. Why would you have to do a microscopic if the blood pad tests positive?
Well, you don't want blood in your urine. I mean,
you have to verify that it's red blood cells, right. So you will see that on the microscope. Protein, as we're going to talk about today, if protein is positive, pretty good indication that there could be blood in the urine. And also, we're going to talk about cast and mucus could be in the urine that'll show a protein positive. If your nitrite's positive, what we learned from just a minute ago.
Bacteria.
So you should see bacteria. What those physicians want to see is they want to see that when you dip that urine, the nitrite pad was positive, and then you saw bacteria underneath the microscope. See how it's correlated. Everything's making sense. Of course, leukocyte esterase, that means there's white blood cells in the urine. Possibly glucose. I told you about this earlier. What might you see under the microscope if the urine specimen has a lot of glucose in it? You could see a yeast infection. Every time? No. In some hospitals, they don't even, like I said, you can have 4+ glucose and you don't have to do a microscopic on it. Now, all the stuff we're going to talk about today, I'm going to talk about some stuff that is very rare that you may not see, but don't lose sight of the big picture. Generally, in urinalysis, you're dipping urines, checking for urinary tract infections, okay? Usually. And that doesn't mean that you won't see all kinds of other stuff, but that's the big picture. So, if you learn anything from this class, you need to be able to look at urine underneath the microscope and be able to see what white blood cells look like and bacteria. Some of this other stuff you'll get with time, but you gotta know what white blood cells and bacteria look like, because if you have that on the microscope and you don't see it, okay, that patient goes home without being treated because you didn't call it, right? The other thing about urines that the book is going to tell you, there's a section in this chapter on microscopes. That's what this class is called, technically, is microscopy, okay? So you have to be really, really good at the microscope. I'm not going to cover a lot about the microscope in this chapter other than key things that I want you to know, because you're going to be tested on the microscope in lab, okay? For your first lab practical, the most weighted point question there is I'm going to hand you a microscope slide with urine sediment on it, and I'm going to give you like 35 seconds to get it in perfect focus and show me. In other words, I got to know when you leave here that you can get the microscope in focus. It will not only be on your first practical, the same thing will be on your second practical, because that's one of the things that clinicals have told us. And I think they tell every MLT or MT program that, is that the students need to be better on the microscopes. They don't want to hand you a slide for a gram stain and you have to take 3 or 4 minutes to get it in focus. So we're gonna really work on our microscope usage. Plus, urines are hard to get in focus. You gotta use low light. And as I'm gonna demonstrate to a lot of you in the lab, I'm actually gonna put you on a microscope, and I'm doing it on purpose. And I want you to look at me and say, there's nothing in this urine sediment. And I'm gonna change the light and show you that there were red blood cells too numerous to count, white blood cells 50 to 100, calcium oxalate crystals, and I'm gonna prove to you that if you use the wrong amount of light, you would have called that urine negative. Okay? All right, another good chart to look at is table 6-1 at the bottom of 100, and it talks about screening tests and the significance and what should cause you to have to do a microscope. Again, that's a quick reference guide. If you look at that box, color can indicate blood, clarity can indicate hematuria versus hemoglobinuria, blood, you would see red blood cells, red blood cell gas. So that's a good reference guide to study. All right, specimen preparation. Everything we're talking about in this chapter is microscopic. So in the right-hand column on page 100, toward the top, specimen preparation. It says specimens should be examined while fresh or adequately preserved. The very last sentence in that section says care must be taken to thoroughly mix the specimen prior to decanting a portion into a centrifuge tube. So you get a urine in a cup, swirl it around, pour it over into a conical tube, and to do the microscopic, of course, we're gonna have to spin that in a centrifuge. Now, you don't spin it and then dip it, okay? You gotta dip it while it's mixed, right? You take that conical tube and mix it, swirl it. But, well, I mean, I'm just saying, if you get in the habit of always spinning it first, you may kind of screw up and spin it and then dip it. But think about what you're doing, use your noggin, right? If you spin it, everything's at the bottom of that conical tube. So some of the things that should have been detected are at the bottom and your dipstick won't touch it. So you could get false results for that. All right, specimen volume. Right-hand column, about halfway down on page 100, says the standard amount of urine, usually between 10 and 15 mils, is centrifuged in a conical tube. Skip a line, it says a 12 mil volume is frequently used because multi-parameter reagent strips are easily immersed in this volume. Next paragraph, if obtaining a 12 mil specimen is not possible, as with pediatric patients, the volume of the specimen used should be noted on the report form. So I want to talk about something. If I have two conical tubes, I have a cup of urine and I've got two conical tubes. In this conical tube, I pour it all the way up to the top. In other words, this is urine, okay? There's a second conical tube. Let's say somebody, they don't get much specimen and they pour urine and it's half of that, okay? Let's just say this is 12 mils, this is 6 mils. Everybody agree with that?
Mm-hmm.
Do you both agree that if I spin these in a centrifuge, and then when I get finished spinning, in this one, I'm gonna have a cell button that looks like that, and this one I'm probably gonna have a cell button that looks like that.
Mm-hmm.
Everybody agree? Because I've got more chance for the solids because I got a bigger volume here than here. So what will happen a lot of times is if we look at these two specimens on a microscope, do you agree we're gonna see double the amount of cellular things in this one than we will in this one?
Yes.
Okay? So that means you report out different results. Like I'm saying, okay, I saw heavy bacteria in this and I only saw moderate bacteria in this, right? It's the same specimen, but it's just because I filled this one up with 12 mils and I only had 6 mils to use here. So some facilities, not the one I worked at, but some facilities, if you have a limited amount of specimen, they want you to footnote it. Like, look, we didn't have much to work with. There was only 6 mils of urine. And that'll tell the physician, well, maybe there's actually more stuff there. They just didn't have much fluid to work with. So you need to understand that concept there. You need to start off with the same amount of urine. And in fact, that's what we're fixing to talk about. We're fixing to talk about standardization. You will have different results if you use a different size drop that you put on your microscope slide, if you use a different size cover slip from specimen to specimen. So when you work at an institution, you need to make sure that everything you do on a urine specimen, to the best of your ability, is done the same exact way. Like every single urine specimen needs to start off, whatever your rules are, if you wanna say 10 mils in every conical tube, you need to pour over exactly 10 mils, okay? And we're gonna go through here talking about standardization. Okay, specimen volume on page 100 in the right-hand column. Just make sure that you know 10 to 15 mils is adequate. Usually spend about 12. Under centrifugation, we need to talk about centrifuging urine specimens. The sediment that's in urine specimens is delicate, okay? If you spin a urine specimen as fast as you spin a blood specimen, you are going to damage all the cellular elements in the urine, okay? Just think of them as fragile. Just think of the white blood cells and the red cells that are in a urine specimen, and if you spin them too fast, just think they all bust, okay? So we gotta spin our centrifuges at a lower rate of speed. The book tells you this, and just kind of try to remember this number. It's gonna tell you to use 400 relative centrifugal rate per minute, I think is what it says, a speed of 400, which basically just means that rotor head, guys, is not spinning as fast as the rotor head that's spinning blood. Everybody see that?
Yes.
On the centrifugal force under centrifugation, make sure you have like the first 5 lines of that highlighted. It says the speed of the centrifuge and the length of time the specimen is centrifuged should be consistent. Centrifugation for 5 minutes at a relative centrifugal force of 400 produces an optimum amount of sediment with the least chance of damage to the elements. Sediment preparation, page 101. I'm at the very top of page 101 under sediment preparation. It says a uniform amount of urine and sediment should remain in the tube after decantation. Volumes of 0.5 and 1 mil are frequently used. So what it's saying is in a conical tube, after you spin it down, you know how like in blood bank yesterday, we were having you guys pour off when you were doing your washes. Okay, whatever way you choose to do it, you need to have the same amount of urine that's basically mixed in with your sediment. When you spin a conical tube, what's gonna happen is you're gonna have this much sediment, and usually you'll have about that much urine with it. You see what I mean? Because you're gonna put that squeegee in there and you're gonna mix it up, all right? Think of this as like sand, and then think about you've got maybe half a mil of water in with, or half a mil of urine in with your sand. So you're gonna put a squeegee in there and you're gonna mix it up. And you really don't have that much to work with, but you got about 10 drops, right? But you don't need but 1 drop on that microscope slide to observe the sediment. So what it's saying is if I use half a mil, okay, and then Bianca, for whatever reason, she likes to put a whole lot of urine in her. You said, I mean, like 3 mils, the results change from Bianca to myself, right? Because I only had a half a mil, and Bianca chose to leave about 2 mils in there.
And so when you're looking under the microscope like yours, you're going to see analytes that are closer together because it's more concentrated rather than Bianca and hers is going to be more further apart. And it'll be easy for you to see and investigate your sediment than it would be for Bianca.
Yes, and the results change because see, when you're looking at that sediment, you're counting stuff. So Bianca's not gonna have as high of a count. She may be seeing 5 to 10 red blood cells per high power field, but because I didn't have as much liquid in with my sediment, when I put my drop on the microscope slide, I may be seeing 25 to 50 red blood cells per high power field. See what I'm saying? The results are different, but it's the same patient. So, you know, I'm leading to something, guys, when I talk about it, but again, a long time ago, when I worked, we just didn't care. We just put urine in a conical tube, we spun it down, we poured off the supernatant. One time I might have half a mil in there, another time I might have a mil in there, but the results can actually change because of that. So through technology, okay, And because people started saying, hey, Rick's results aren't matching JJ's results. It's the same specimen, and I know they're both good techs, and I know they both know what white blood cells are looking like, but JJ got a result of this, and Britt got a result of this. So all of these companies that make urinalysis supplies, they figured out a way to standardize looking at urinalysis. So, perfect example, where I worked at, I would take a microscope slide, I would put my squeegee in that sediment gook, and I'd put one drop on the microscope slide, and I'd put a cover slip on it, okay? Sometimes I'd use a big drop, sometimes I'd use a little drop, just depending on how I felt that day, okay? And sometimes my drop would be so big that I would actually see fluid kind of come out from underneath the cover slip. You see what I mean? Like I put too big of a drop on there. So they developed these things called Cobra slides.
Oh,
Okay?
yeah.
And I don't know if you guys can see it from where you're at, but they look like little half moon shapes, all right? It doesn't matter how big of a drop you put in there because it is graduated to only hold a certain amount of sediment. You see what I mean? Like when you put it, every one of those is calibrated to the same amount. So even though I put a big drop in there, if there's any excess, it's gonna kind of come out the top. I'm looking at the same amount of sediment. So as we read over this stuff, you just have to do things on every single specimen the exact same way. Now, let's say your lab, like a lot of labs, don't want to pay what these things cost because these are expensive. One thing that kind of makes these efficient is if you look at this, you notice there's what, 5 bubbles, 5 half moons on there's 10 half moons on this. I can do 10 different microscopics on it. It would take me 10 microscope slides for this. Okay? And what we would do in the lab when we would use these is when we got finished with them, I'd take my black Sharpie and put a line through it. So I would know I've already used that one, okay? But if your lab refuses to pay for these, but again, they're expensive and they want to use microscope slides, the best advice I can tell you is first of all, use the same size cover slips every time, either a 12 by 22, 25 by 50, whatever your lab uses. Don't use different sizes, okay? Use the same type of slide, the same type of cover slip, and you can always decant the same amount every time. You see what I mean? Like if you can use conical tubes that have a volume on the side of it, and that way you can say, okay, every single time I'm only gonna leave 1 ml of urine with the sediment, right? And you can, for example, instead of getting a squeegee like I always used to do and putting a drop on the microscope slide, you can mix it up and then maybe get a pipette and pipette out exactly 20 microliters of sediment every time. In other words, everyone's drop will be the same exact volume. Standardization, it makes it more efficient and it makes your results be reproducible every time. So I pretty much just explained to you sediment preparation, volume sediment examined. Under commercial systems, make sure you have highlighted there. I'm in the left-hand column on page 101, go down to commercial systems at the bottom. It says the conventional method of placing a drop of centrifuge urine on a glass slide, adding a cover slip and examining microscopically has been substantially improved through the use of commercial slide systems. That's what I just showed you. I call them COBA slides. Stand right there. And make sure you have the word standardization. That's the next line down. Okay, page 101, right-hand column, a little less than halfway down under examining the sediment. So the microscopic examination should be performed in a consistent manner and include the observation of a minimum of 10 fields under both low and high power. So pretty much whatever we're looking for, when you look in the microscopic, there's gonna be things every time you look at a microscopic, you're looking for red blood cells, you're looking for white blood cells, you're looking for bacteria, you're looking for yeast, you're looking for trichomonas. Anything that pops out at you. So let's just say I'm looking under high power. That means 40 on a microscopic. And let's just say this is my field of view. And let's say I'm under high power and I see 5 white blood cells, all right? And then I go, okay, I counted 5 in that. So I go to the next field, and let's just say that not as many. I count 2, all right? Technically, you're not supposed to take an average until you have counted 10 fields, all right? That's for everything, not just red blood cells. You've got to be keeping in mind white blood cells, red blood cells, all of that type of stuff. The textbook answer for that is you have to view at least 10 fields. Put that answer on the exam, okay? Now I'm gonna tell you real world though. In real world, you don't have time to look at 10 fields. You're not gonna be able to look at 10 fields and take an average for white blood cells. Look at another 10 fields and take an average for red blood cells. I mean, I could probably get in trouble for telling you this, but I'm just saying, even and I've done a lot of them, if I honestly abided by that code, it would probably take me an hour to do every single urine specimen, looking at it underneath the microscope. So what will happen is you'll look at a field, you'll glance down at it, you'll see this, and you won't even count them, okay? You just look and you'll see it. You'll go to another field and you'll see it. And you'll get to where you're not, I mean, I know you may not believe me, but you're truly not even counting them. You'll go to the next field, and let's just say you see 10 in there, okay? When you go, now we're talking about red blood cells right here, when you go to put your answer in red blood cells, if I'm seeing stuff like this, okay, there's a drop-down box under red blood cells, and you have choices. The first one is gonna be NS, for none seen, for example. The next one is going to be 0 to 2. The next one's gonna be 2 to 5, and then 5 to 10, 10 to 25, 25 to 50. You'll even have an option that says TNTC. What does that stand for? Too numerous to count. They're everywhere. In other words, I can't count every one of those unless you want me to spend 8 hours on it.
Right.
So like if I'm doing that, unless I see a field that goes crazy on me, I'm already thinking 2 to 5. 2 to 5 for a high power field. You see what I'm saying? Because I looked at this one, I saw 5, I saw 2, I look at the next one, as long as it's falling in the back of my mind, okay, 2 to 5, 2 to 5, 2 to 5. That's generally how techs count them. But on your ASCP registry, I want you to say, you have to count a minimum of 10 fields and take the average. But that's almost impossible, because you would literally have to write down that I saw 25 in this field. I saw 41 in this field. You see what I'm saying? You won't have time to do that, because now you gotta count white blood cells, and you gotta just keep going with all the elements that's in there. But you do have to take an average. So you'll develop your own way to do this, but I just want you to keep in mind that when you're working in a laboratory, you're doing lots of urines. You don't just have, you don't do 3 hours in one day and you got 8 hours to do 3 urine sediments. You've got a lot of other stuff going on. And it's not that you're gun decking it. Gun decking is like a word like you're lying, okay? But what you're doing is that you have to be efficient enough to where you can report those results out quickly. Now remember, this is high power field, so when you look at one field, kind of glance at it, look at what's going on, like, okay, I see whites, I see reds, I see a sperm over there, I see yeast down there, I see a hyaline cast up there, and I see a squamous epithelial cell there, okay? Then go to the next field. In other words, move your slide to a completely different field. And then look at all that stuff again and get an idea of a good estimation of how many are in each field. Most everything is quantitated, or you do your count on 40 power. That's called high power on a urinalysis microscope. There's one thing that I can think of right off the bat that you count on low power. That's 10 power, not 4. Okay, in urinalysis, 10 power is low, 40 power is high. You will never use the oil immersion in urinalysis. Okay, unless I tell you different. So cells, bacteria, sperm, parasites, yeast, all of that stuff is quantitated on 40 power. The only thing that I know of that's counted on 10 power, and I think it backs me up in your book on this, is cast. You remember in the intro class, I told you there's something called cast you'll see in the microscopic that's kind of like, it'll be like this. That's a cast. Those are so big, you don't wanna count those on high power because you're not seeing enough of the picture, so you count those on 10. Let's go ahead and get out of the way, because I know this is on your test. There's a question like this on your test. Total magnification. A lot of these pictures that we're gonna look at today, when I say, look at this picture figure so-and-so, that is yeast, okay? And if you look underneath it and read it, it says that's magnified 400. Okay? That used to confuse me, actually, when I first started teaching, because I'm like, where are they getting these 400 power objectives, okay? What are they talking
40.
about?
You have to multiply.
That's
Yeah,
right.
Okay.
Okay, exactly.
40 times
They're
10.
talking about, they're looking at it on 40 power, but they're multiplying times the oculars that are also 10
10
power.
power.
So under a lot of these pictures, it's gonna say 400 power, that's what they're meaning.
Okay.
Some of the pictures is gonna say 100 power, but it's not the oil immersion objective they're using the 10 by, okay, and the oculars, that makes 100.
Because oil immersion is 1,000.
Yes, oil immersion objective is actually magnified times 1,000, is what you're looking at. Good. So you guys, that's another question you guys will already get right. Total magnification is whatever the objective is times the oculars. Now, before we go to break, and I think this will say it somewhere else in your book, when we do cells, you quantitate them by a number. Like, for example, if you're looking at a sediment and you don't see any red blood cells, but you see white blood cells, it's gotta be assigned a number. Hopefully, you'll have a drop-down box that kind of gives you a range, you know, again, 2 to 5, 10 to 25, 25 to 50. One of the options we had was greater than 100, but then after that one, it would be TN2C. I know that's kind of the same thing, but that's what we would have. But there's some things that you just absolutely cannot count, like bacteria, okay? So when you report out bacteria on a urinalysis result, depending on where you're working, I know we always reported out none, rare, few, moderate, or many. Okay, so you could just say a few bacteria. That means you're seeing a few in every field. Many would be, they're everywhere, okay? And they can also do it on a plus system. They can do none seen, 1 plus, 2 plus, 3 plus, 4 plus. Is Haley's 4 plus gonna be my 3 plus? I mean, it could be, you know what I mean? You're guessing, but bacteria is guessing. I mean, any physician, I would think, if I put 3 plus and somebody else puts 4 plus, okay, it's still a urinary tract infection.
Yeah.
They're not gonna like say, well, 4 plus, I'm giving this much antibiotic, 3 plus, they're not gonna change their minds on that. So things like bacteria, squamous epithelial cells, a lot of times, they may report out as few, moderate, or many. Crystals, they usually report out like 1 plus, 2 plus, 3 plus, 4 plus. But things that you can absolutely count, like red blood cells and white blood cells, you have to assign a number to it. So everything, for the most part, is counted on high power, except for casts that are usually counted on low power. And one more question that they love to ask on registries, because it's so hard to get urine sediment in focus on a microscope. Once you guys do a few, it's easy, but I mean, right at first, you're gonna hate it, because it's just like, I don't feel like I have any good focus. They tell you, because a lot of urines you look at are negative, okay? For whatever reason, you're being forced to do a microscopic. Let's say it's a pediatric patient, and you have a rule in your lab that says if they are under 10 years of age, you have to do a microscopic no matter what. Or if it's a patient from labor and delivery, you have to do a microscopic no matter what. It doesn't matter if it's yellow and clear and every result is negative. All of the OBGYN doctors that you'll have a note of, it says they want microscopics on every one of their patients, okay? So, if you're looking at urinary sediment and you can't find anything, you don't know if you're in focus or not because you're not seeing anything, right? There's nothing there. There's no red cells. There's nothing to focus in on to make sure that you're seeing what's in there. they will tell you a lot of times to focus in on what's called a squamous epithelial cell. In most urines, not all of them, but on most of them, if you look long enough, you should find an occasional squamous epithelial cell, all right? So this is something that they tell you to initially focus your scope on, because if you get one of these in really good focus, then you understand, okay, there's nothing in here, because I've got a perfectly good squamous epithelial cell in focus, and I'm not seeing anything else, so you know you're in focus, all right? Now, that's not the way I did it, so I'm gonna tell you Britt's theory on this, all right? I would always, like, here's your microscope slide, and here's your cover slip. I would always focus in on the edge of the cover slip and get it in perfect focus. You'll understand, if you can get the edge of that cover slip in perfect focus, you're where you need to be, okay? But the textbook answer is gonna be focus in on a squamous epithelial cell. Just so you have it highlighted in your book, page 101, under examining the sediment, go down to the last paragraph. I think it starts with the word initial focusing can be difficult. Everybody with me? See where it says that, initial focusing can be difficult? You'll go down about 3 lines. It says often an epithelial cell will be present to provide a point of reference. The next section talks about reporting out things, and I just went over all of that on your board. All right, let's take a break. Let's take 10 minutes, guys. We got quite a bit of stuff